Okay, so what do a skyscraper, a spoon, and a satellite all have in common? I know, it sounds like the beginning of a really weird joke, but the answer is actually the secret to, well, most of our modern world. They're all made of metal. But what does that even mean? What makes a metal metallic?
That's the huge question we're going to dig into today. And trust me, we're going to go from a really simple, kind of beautiful idea all the way to some mind-bending materials that are absolutely going to shape our future. All right, let's get into it.
So the whole secret, the one core concept that explains almost everything about metals, has this amazing name, the sea of electrons. And it's a perfect name for a concept that is just as simple as it is powerful. So this is what it looks like in your head. Imagine the atoms in a piece of metal are just super generous. They don't really hold on tightly to their outermost electrons. Instead, they just let them go, releasing them into this free-flowing, negatively charged sea that moves all around the atoms. And because those atoms have now lost a negative electron, they've become positive ions.
And that right there brings us to the official term metallic bonding. It's nothing more than the attraction between all those positive metal ions and that shared sea of negative electrons. The ions themselves, they line up in this neat repeating grid we call a lattice, and that electron sea just acts like this flexible, super strong glue holding the entire thing together.
And here is the really cool part. This one single idea, positive ions floating in a sea of electrons, explains all the classic properties of metals that, we see and use every single day. Let's break down how.
So why do metals conduct electricity so well? Well, it's because that sea of electrons is totally free to move and carry a current. And why are they shiny? The surface of that electron sea literally bounces light photons right back at you. High melting points? That's because the attraction between the ions and the sea is incredibly strong. It takes a ton of energy to break it apart. And being malleable? That's the really clever bit.
Okay, so think about why you can bend a paperclip without it just snapping in two. When you push on it, you're forcing the layers of those positive ions to slide past one another. Now, in a lot of other materials like glass or ceramic, that would cause it to shatter, but not in a metal. In a metal, that flexible electron sea just flows right along with them, instantly reforming the bonds in their new positions. So the metal changes its shape, but the whole structure stays perfectly intact.
But of course, it's not always quite that simple. That sea of electrons model is an amazing starting point, but the real world has some absolutely fascinating twists. See, not all metallic bonds are created equal.
To really get this, let's ask a really specific question. We all know aluminum is strong enough to build an airplane. But pure sodium, which is also a metal, is so soft you can literally cut it with a butter knife. So why the huge difference in strength?
This tells the whole story right here. It all comes down to how many electrons each atom is willing to give up to the sea. A sodium atom, it only donates one single electron. That makes for a pretty weak bond. Magnesium gives up 2, which is better, but aluminum, it contributes 3 electrons, creating a much denser, more negatively charged glue, and that means a much stronger bond. So there's your rule of thumb. The more free electrons an atom donates, and the higher its positive charge becomes, the stronger that metallic bond is going to be. It's a pretty simple relationship, but it has enormous consequences for the kinds of materials we can actually build.
But then, you get the weirdos. Nature just loves to throw a curveball. Take gallium, for example. It's a metal, for sure, but its bonding has a bit of a non-metallic covalent character to it, and that's why it has such an incredibly low melting point that you can literally melt a solid piece of it right in the palm of your hand. And if you want the ultimate exception, we have to talk about mercury. The reason it's the only metal that's a liquid at room temperature, well, it has to do with Einstein's theory of relativity. Seriously, in a super heavy atom like mercury, the electrons are moving so fast that relativistic effects actually cause their orbits to shrink. And that, in turn, weakens the metallic bonding between the atoms enough to make it a liquid. I mean, how incredible is that?
And that kind of weirdness actually brings us right to the cutting edge. Our simple sea of electrons model is great, but modern science has gone way deeper, diving straight into the quantum world to design the materials of the future.
You see, our understanding didn't just stop there, it kept evolving. That sea of electrons idea is a fantastic starting point. It's pretty similar to what was called the Drude model back in 1900. But to really truly explain how electrons behave, scientists had to bring in quantum mechanics, and that eventually led to what we now call band theory, which gives us a much more powerful and accurate picture of everything going on inside a metal.
And having this deeper understanding lets scientists get really creative. For instance, high-entropy alloys.
Think about traditional alloys, like bronze. You're just mixing 2, maybe 3 metals. With these new alloys, scientists are mixing 5, 6, even more different metals together in equal parts. This just completely scrambles the normal, neat crystal structure, and it creates these totally new bonds that result in materials that are just unbelievably strong and tough.
Then you have something called metallic glasses. Now, imagine cooling down liquid metals so ridiculously fast, we are talking 1,000,000 degrees Celsius per second, that the atoms have 0 time to line up in their usual neat crystal pattern. They get frozen solid in a totally random, jumbled state, kind of like the atoms in a piece of glass. What you end up with is a material with the properties of a metal but the structure of glass, giving it just incredible strength and elasticity.
And believe it or not, it gets even more futuristic. Researchers are now creating 2D metals. These are sheets of metal that are literally a single atom thick. It's wild. When you force electrons to live in a flat, two-dimensional world like that, they start behaving in really, really strange ways. And those bizarre quantum properties are exactly what scientists are hoping to use for things like next-generation quantum computers.
So, from a simple sea of electrons all the way to materials that sound like they're straight out of science fiction, the story of the metallic bond is really the story of our technology. It really makes you wonder, the next great technological leap, it might not be written in software at all. It might be forged in a metal that we haven't even invented yet. What do you think we'll build with it?